Welcome back to Paper AI. Today, we are exploring a groundbreaking paper that changed the face of computer vision and deep learning as we know it as Alexnet. Hi, I'm Ravi with my teammate Lisa, and today, we are going back to 2012 to uncover the revolutionary work behind Alexnet. This model, formerly known as ImageNet Classification with Deep Convolutional Neural Networks, was proposed by Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton and presented at the prestigious NIPS conference in 2012. In this video, we'll break down Alexnet's design, innovations, and impact on the field. We'll explain why this model was so influential, especially in how it dominated the ImageNet Large-Scale Visual Recognition Challenge, or ILSVRC, with unprecedented accuracy. So, whether you are a seasoned AI researcher or someone curious about deep learning's origins, get ready for an in-depth exploration of the architecture, training strategies, and unique features that set Alexnet apart.
Hi, this is Lisa. Now we are exploring contributions. Let's break down Alexnet's major contributions and compare them to previous models, like LeNet-5, and the models that followed, such as VGG, GoogleNet, and ResNet. First, let's talk about depth and complexity. Earlier models, like LeNet-5, only had a couple of convolutional layers, which limited their ability to capture complex patterns in images. Alexnet, on the other hand, introduced a much deeper network, with 5 convolutional layers and 3 fully connected layers. This deeper architecture enabled Alexnet to extract more sophisticated features, allowing it to classify more challenging, high-resolution images. Later models built on this by going even deeper. For instance, VGG16 has 16 layers, and ResNet introduced an astonishing 50-plus layers with the help of residual blocks. But Alexnet paved the way, proving that deeper networks could improve accuracy. One of Alexnet's key contributions was its use of the ReLU activation function instead of traditional tanh or sigmoid functions. Tanh and sigmoid could cause vanishing gradients, making it hard to train deep networks effectively. By introducing ReLU, Alexnet improved gradient flow, speeding up convergence and making it possible to train deeper networks. This was a game-changer for deep learning, and now ReLU is a standard across nearly all neural networks. Since then, ReLU has been further refined with variants like leaky ReLU and PRELU to address some of its limitations. Another groundbreaking advancement was in the input image size. Previous models, like LeNet-5, were restricted to small, low-resolution images. Alexnet expanded this to handle 227 by 227 RGB images, enabling the model to tackle more complex, real-world images from the ImageNet dataset. Successor models like VGG and GoogleNet also adopted large input sizes, with some even moving to higher resolutions. To preserve critical features, Alexnet introduced max pooling rather than the average pooling used previously. Max pooling helps retain essential information in images, and Alexnet also added local response normalization, LRN, layers to enhance generalization and stability during training. While later models like GoogleNet experimented with different pooling strategies and sometimes dropped LRN. Alexnet's innovation here was critical. Alexnet was the first to introduce dropout in the fully connected layers. Without dropout, models were prone to overfitting, especially when working with large datasets. Dropout dramatically reduced this risk by randomly dropping some neurons during training, making the model more robust and generalizable. Since Alexnet, dropout has become a common regularization method in neural networks, with successors also adopting techniques like batch normalization. Data augmentation was another innovation Alexnet brought into the spotlight. By applying transformations like flipping, cropping, and color variation, Alexnet was able to make its model more resilient and robust, helping prevent overfitting. Data augmentation remains a core part of training even today, with advancements like cut mix and mix-up that go beyond basic transformations. Finally, Alexnet was one of the first models to leverage GPUs for large-scale training. With the NVIDIA GTX 580 GPUs, training times reduced from weeks to days, making it possible to train large, deep networks on datasets like ImageNet. This was a massive leap forward. And today, GPUs and TPUs are standard in deep learning, enabling models that are larger and more complex than ever before. In summary, Alexnet introduced innovations across depth, activation functions, image size, pooling, regularization, and hardware utilization. These advancements formed the foundation for modern computer vision and deep learning models. Alexnet didn't just win the ImageNet challenge. It opened up new possibilities for what neural networks could achieve.
When we talk about popular preceding models, those are: in 1980, the neocognitron introduced the first hierarchical convolutional structure designed for pattern recognition tasks. Despite being innovative, the neocognitron was limited in scalability and struggled with complex image datasets. It also lacked techniques like ReLU activation and dropout, which Alexnet would later use to improve training efficiency. LeNet 5 by Jan Lacan was one of the first neural networks to use convolutional and pooling layers and was designed for digit classification. While LeNet 5 was a huge step forward, it had a shallow structure and was limited to small, low-resolution images. Its reliance on sigmoid and tangha activations led to slower training and vanishing gradients. And the importance highlighted in Alexnet are: as its use of max pooling over average pooling helped improve feature extraction. Max pooling preserved the most significant features in each region, enhancing the model's ability to detect edges, textures, and patterns, which are crucial for accurate image classification. Alexnet, introduced in 2012 by Geoffrey Hinton and his team, was revolutionary for its time. It made deep learning feasible at a large scale by harnessing the power of GPUs. This architecture consists of 8 layers, 5 convolutional layers, and 3 fully connected layers. Alexnet paved the way for deeper networks, and each element was purposefully designed to capture more complex patterns and improve accuracy. We'll compare Alexnet to its successors, covering aspects like the number of layers, convolutional filters, stride, padding, and more. Alexnet began with large filters in early layers, such as 11 times 11 filters. This choice was later refined by VGG and ReLU, which used smaller filters like 3 times 3 across more layers to capture finer details and add depth. DenseNet's densely connected architecture reduces the need for high numbers of filters, promoting parameter efficiency. Stride and padding influence spatial resolution. Alexnet had a high initial stride of 4, which reduced spatial dimensions but sacrificed some detail. Later models used a stride of 1 and same padding, preserving image details while allowing the network to deepen. Pooling layers help lower computational costs and allow the model to generalize better. Alexnet and VGG used max pooling, focusing on capturing prominent features, while ReLU and DenseNet adopted average pooling, keeping finer details intact. Fully connected layers consolidate spatial data for classification. Alexnet used 3 dense layers, which demanded high parameters. GoogleNet, ReLU, and DenseNet minimized the number of fully connected layers, focusing instead on efficiency and reducing parameter count. Parameter count impacts model size and training requirements. Alexnet had around 60 million parameters, which was massive at the time. VGG went even higher, with 138 million. Successors like GoogleNet and DenseNet reduced this count, improving efficiency and making training more feasible on single GPUs. Alexnet didn't use batch normalization, but this feature became critical in later models. It standardized inputs within mini batches, stabilizing training and enabling faster convergence. ResNet and DenseNet extensively use batch normalization to improve accuracy. Residual connections, introduced in ResNet, allow gradients to bypass layers, solving the vanishing gradient problem in very deep networks. DenseNet's dense connections take this further, connecting each layer with all preceding layers, promoting feature reuse and efficiency. So, what did we learn from Alexnet and its successors? Each model has contributed something unique to the evolution of CNN architectures. Alexnet introduced us to deep networks with GPU acceleration. VGG demonstrated the power of small filters for deeper networks. GoogleNet's inception modules allowed multiscale feature extraction, while ResNet's residual connections solved deep network challenges. DenseNet's dense connections optimized feature sharing, reducing parameters without sacrificing accuracy. Alexnet's impact on deep learning is undeniable. Its architecture set a foundation that modern networks have built upon, refining the balance between depth, efficiency, and accuracy. As CNNs continue to evolve, these innovations pave the way for even more powerful and efficient models. So, what makes Alexnet special? It's an 8-layer convolutional neural network, or CNN, designed to process large datasets like ImageNet. Alexnet starts with an input image size of 224 by 224 pixels and is built with 5 convolutional layers and 3 fully connected layers. Let's look at the first convolutional layer. It takes the input image and applies 96 filters of 11 × 11 size, each with a stride of 4. This helps Alexnet capture key features while reducing spatial dimensions. Then, it uses ReLU activation, a fast and simple nonlinear function that lets Alexnet learn more complex patterns. The first convolutional layer is followed by max pooling, which reduces computational complexity while preserving the most significant features. This cycle of convolution and max pooling continues through layer 2, where we have 256 filters of 5 × 5 size with a stride of 1, then 384 filters in layer 3. These steps help Alexnet detect features like edges, textures, and shapes. By layer 5, the network applies 256 filters of 3 × 3 size, preserving spatial details critical for classifying objects accurately. After the convolutional layers, Alexnet uses fully connected layers, each with 4096 neurons, to combine these learned features for classification. Both of these layers use ReLU for activation, and Alexnet also incorporates dropout regularization, where 50% of neurons are randomly turned off during training to reduce overfitting. Finally, the model outputs a 1000 class probability distribution using the softmax function, which selects the most likely label for each input image. What made Alexnet innovative wasn't just the architecture, it was the training approach. Alexnet leveraged GPUs, NVIDIA GTX 580S to train faster, harnessing parallel processing for a dataset as massive as ImageNet. Alexnet also uses data augmentation techniques like image translation, horizontal flipping, and color jittering to prevent overfitting and improve generalization. These techniques allow Alexnet to perform well on real-world images. In 2012, Alexnet achieved a top 5 error rate of 15.3%, a huge leap compared to prior models. Its success laid the groundwork for future deep learning research and models, pushing the boundaries of what AI could achieve in vision tasks. Alexnet was more than just a model, it was a breakthrough, proving the power of deep learning on complex datasets. Its influence can still be seen today in modern architectures. The journey of working of this model begins with the input layer. The image is resized to 24 times to 24 pixels, normalized by subtracting mean RGB values and zero-centered, preparing it for processing. Output dimensions remain to 24x to 24x3. Next, the first convolutional layer applies 96 filters of size 11 × 11 with a stride of 4 and no padding. This extracts basic features like edges and patterns. The output is a 55x55x96 feature map. A 3x3 max pooling operation with a stride of 2 reduces the spatial dimensions, resulting in a 27x27x96 feature map. Convolutional layer 2 applies 256 filters of size 5 × 5 with padding of 2 and a stride of 1. ReLU activation is applied, creating a 27x27x56 feature map that captures complex textures. Another max pooling layer reduces the size further to 13x13x56, preparing the data for more detailed feature extraction. The next 3 convolutional layers refine the features. They use 3x3 filters with padding of 1 and strides of 1, producing feature maps of 13x13x384, 13x13x384, and 13x13x56, respectively. The final max pooling layer reduces dimensions to a compact 6x6x56, creating a feature map ready for classification. The feature map is flattened into a vector of size 90 to 16 and connected to 4096 neurons in the first fully connected layer. ReLU activation is applied. To prevent overfitting, 50% of the neurons are randomly dropped during training. The next fully connected layer connects 4096 neurons to another 4096, applying ReLU activation again. Once more, dropout regularization is applied, reducing overfitting and improving generalization. The final fully connected layer connects to 1000 neurons, each representing a class. Softmax activation generates probabilities for classification. The output is a probability distribution over 1000 classes, with the highest probability indicating the predicted class. For example, in this case, it's a cat dot. This pipeline demonstrates how Alexnet processes an image, layer by layer, to extract features, reduce dimensions, and classify it with remarkable accuracy. What makes Alexnet to outshine Alexnet is highly efficient for low-resource devices. Its fewer parameters make it suitable for IoT and edge devices with limited computational power and memory. In contrast, models like VGG and ReLU demand more computational resources, making them less viable for such environments. For time-sensitive applications like real-time object detection, Alexnet's faster processing and fewer layers make it a winner. Heavier models, such as ReLU, may struggle to meet real-time requirements due to their higher computational demands. Alexnet excels at generalizing on small datasets. Its simpler architecture avoids overfitting, a challenge faced by deeper models like VGG, which often require larger datasets to perform effectively. With its straightforward architecture, Alexnet is a great tool for educational purposes. It's easy to understand and implement, making it ideal for beginners. On the other hand, complex models like ReLU or DenseNet might overwhelm those new to deep learning. Alexnet can be fine-tuned for specific tasks even on low-end hardware. In contrast, larger models require high-performance GPUs, making them inaccessible for environments with constrained resources. When working with small datasets, Alexnet performs well without relying heavily on data augmentation. Larger models, however, need significant augmentation to achieve comparable performance. Alexnet's simplicity allows it to be implemented quickly for prototyping and benchmarking. In contrast, more complex models require substantial resources and time, making them less suitable for rapid experimentation. To sum up, Alexnet shines in applications requiring low resources, real-time performance, or small datasets. It's perfect for learning, prototyping, and general-purpose tasks, especially when resources are limited. Thank you so much for watching this detailed explanation of the Alexnet paper. I hope this helped you understand the concepts more clearly. If you found it useful, don't forget to like, share, and subscribe for more AI paper breakdowns. Your support keeps us motivated to bring you the best content. See you in the next one. Stay curious and keep learning.